writing the equation of a line, but a vector equation. Now, in 2 dimensions, we have a lovely equation of a line. 3 dimensions, it changes a little bit. So let's look at it in 2 dimensions first, and then we can push the idea through to the 3rd dimension. The vector equation of a line rather than the Cartesian equation that we normally see. So, all right, in 2 dimensions, here's our vector that I've drawn in there. I've labelled 3 points on that vector. 2 of them I know. So A and B are points I know on that vector. R is just any other further point on the line. So R will give us the equation, if you like, because that's the random point. And their position vectors I've logically called A, R and B. So R is on that line. Now if that is true, then the vector AR must be some multiple of the vector AB. They're going in the same direction, they've just got different lengths. So that scalar multiple is just some real number. Well, vector AR would be head minus tail, so R minus A. And then we're going to say it's lambda times B minus A. Remember, it's the vector equation of R we're trying to find. That's the vector equation of the line. So I just make R the subject, and we have our formula. There it is. R would equal A plus some multiple of whatever B minus A is. So that is what we call a vector equation of the line. Now, if I was to give the coordinates of A and B, so x1, y1, x2, y2, what we normally see, I could write it like this. Now I've done them as column vectors, but R would become the random point, xy, the one I'm trying to find. x1, y1 is a point that I know is on the line, but B minus A. Essentially, this is the slope of the line, but written slightly different. Because of course, normally with the slope of a line, we see rise over run, so the y values would be on top. But because I'm writing it as a column vector, the x's remain on the top. This is what we call the direction vector. It's the direction the line is going. So looking at the parametrics, x would equal x1 plus lambda times x2 minus x1, and a similar expression for y. So there are parametric equations for the line. What do they have in common? They have in common this lambda. So I could say lambda equals, well, if I use the first one, it'll be x minus x1 over x2 minus x1. And if I use the second one, it'll be y minus y1 over y2 minus y1. That actually is the Cartesian equation of the line, but just written a little bit differently to what we see. See, normally we don't have this equals some constant number. That will become useful when we go to 3 dimensions. We forget about the lambda. You can see we create the point slope formula. That's where it comes from. So if it now asks me to write the vector equation of the line, so not the Cartesian equation of the line, the vector equation of the line, passing through these 2 points, I can now write it very quickly. That's all I've got to do. Because it's going to be random point x, y. I just need a point on the line. Well, I've used 3 minus 5, but I've put the position vector for that down, plus some multiple of the direction vector. And the direction vector is just the difference in the x values over the difference in the y values. It doesn't matter which way I go because I'm multiplying it by this constant number at the front. So I could have gone, what would it be on the top? I could have gone minus 2 minus 3 is minus 5, but then I'd have to do the y's in the same order. So I'd have minus 8 minus 5, which is minus 3. Well, that's just a negative of what I've got. I could easily factorise the negative, and then lambda would just be negative instead of positive. Of course, I could have written it this way. It could be any point on the line I like. So another point I knew was minus 2, minus 8. That would be one as well. So the difference, I guess, between Cartesian equations of the line and vector equations of the lines, there is one Cartesian equation of the line. But we can have many different vector equations for the same line, because I could pick any point on the line I like. But this is the important thing. That is the actual Cartesian equation of the line. The thing to note is the slope. See how the slope of the line is 3/5? Look at the direction vector, 5 on 3. So you can think of it like it's the slope upside down, and is the direction vector, which means 2-dimensional ones become real easy. Here's an interesting thing. Let's go back to complex numbers. And remember we said multiplication by I is rotation of 90 degrees. So when we talk about the slope, we talk about, well, now with direction vectors it's run over rise rather than rise over run. So if I'm going to rotate this vector, if its direction vector is run over rise, I'm going to multiply it by I, which should mean its rotation of 90 degrees. Well, if I rewrite run over rise in component form, I'd get run plus I rise. I'm going to multiply that by I, and I get I run minus rise. Put that back into a column vector, and I end up with minus rise over run. AB is perpendicular to minus B over A. That's what we're saying. Now, using the dot product, I can confirm that yes, indeed, because those two things do multiply together to give 0, they would be perpendicular to each other. Just an interesting side note there. Okay, let's go back to this. They've given us the Cartesian equation. We have to find, and notice it says a vector equation, not the vector equation, because again, there's many different answers you could give here. And I can just write it down. I just have to find a point that's on the line. That's easy enough. I just pick a value, sub it in, and get the y value. And then the direction vector, slope upside down. So any point that lies on the line, reciprocal of the slope. Looks like it. Don't put the fraction bar in though. Leave that out. Find the point of intersection then of these two lines, which we would have done via simultaneous equations. Well, I can now say the vector equation for the first one there, and I've picked the point 0, negative 1, but that would be my vector equation. For the second one, 3, 0. Yeah, I made it easy for myself. I made sure one of the numbers was 0. It's always an easy number to work with. But hang on a sec, it's the point of intersection. So therefore, if I read the components, I get that lambda is 3 plus 5 mu. But then I can also say minus 1 minus 2 lambda is minus 3 mu. Basically, I'm saying, I'm equating the components. I read across here, and I read across here. Well, solving that, I get that mu is negative 1. And now I know what mu is. I can substitute that in to our second one, and I get the coordinate straight away. Minus 2, 3. Find a vector equation joining these two. Then use that to write parametric equations. And then we're going to find the point where that line meets the parabola y equals x squared. Okay. Equation of line, that's nice and easy. Pick a point, minus 1, 1, nicer numbers than 4, 11. And the slope, now you might be looking at this thinking, hang on, you got 1 over 2, but the difference in the y values is 10, and the difference in the x values is 5. Well, yeah, sure, I could have written 5 over 10, but it's any multiple of it. So it makes sense to simplify it down. So I'll write it as 1 over 2. So reading across, I know x is minus 1 plus lambda, y is 1 plus 2 lambda. But it intersects with y equals x squared. So if I sub those in and solve, I get 2 possibilities for lambda. Now I can go back and get the points. Because if I sub 0 in, I get minus 1, 1, which by coincidence is the point they gave me. But if I sub 4 in, I get 3, 9. There's the other point where it meets. That brings me to last year's HSC. They told us the line was this, and they gave us the vector equation for the line, and they said L2 passes this through this point and is parallel. Find the equation of the line. Well, the direction vector is 3 on 2, so I know the slope's 2/3. I got a point, I got a slope. Thanks very much. How is this extension 2? But anyway, that was in last year's HSC, and it still baffles me. So let's now push this idea through to 3 dimensions. The equation of a line that passes through A and B, well now it doesn't change because the vectors there are dimensionless. So it's still the same idea. R will equal A plus lambda B. Okay. So A is simply any point on AB and B is our direction vector. Nothing's changed. So if I now have to find the equation of a line passing through these 2 points, but there it is. I now have 3 numbers instead of 2. What is the Cartesian equation? Now this is where it's different. There it is. Whoa. Now here is what's unusual. Because I'm dealing with 3 equations, I've got 2 equal signs in there. We don't normally see that. But why? Because we're all equating them to what is lambda? What is the common thing? What is lambda? So each of these components, I'm making lambda the subject. So on the top, I've got x equals 1 plus 3 lambda. Well, if I rearrange that, I get lambda is x minus 1 on 3. I've got y is 2 minus 5 lambda. Rearrange that, I get lambda is 2 minus y on 5. And I've got that z is equal to 3 minus lambda. Rearrange that, we get lambda is 3 minus z. So these three things are equal to each other. So unusual because we have 3 pronumerals instead of 2. HSC question from 2020. They've given us 2 lines. We have to find the point of intersection of the 2 lines. And let's equate. So 3 plus lambda 1 must equal 3 minus 2 lambda 2. Just reading across the x ones. So at point of intersection, their x values must be the same. Therefore, I now know that lambda 1 must equal minus 2 lambda 2. If I now read across the y ones, I get minus 1 plus 2 lambda 1 is minus 6 plus lambda 2. But we just said lambda 1 was minus 2 lambda 2, so I can rewrite that. Lambda 2 is 1. The z ones, because remember, all 3 have got to be the same. Z is 7 plus lambda 1, but it's also 2 plus 3 lambda 2. Oh look, it does turn out to be 1 as well. Just be careful of that. The reason I put it into the third one is to confirm that the lines intersect. Because it could be possible that the x and the y were the same, but z is something different. Now, in this particular question, I probably didn't need to do that. Because we were told that there is a point of intersection. So as we're told there is one, then I really don't need the third component. If I didn't know there was one, because it actually is possible to have the same x value and the same y value, but they don't meet at all. So I would have to check the third one as well. But in this case, didn't actually need to. All right, now we know what lambda 2 is. I'll substitute it in, and we've got our, well, I've found the position vector of the point. What did they ask for? Did say the point, so technically I should have said it was 1 minus 5, 5. Find the vector equation of the line that passes through these. Okay. Now at least that's a bit more interesting than the one they asked in the HSC, which was only in 2 dimensions. But it's the same sort of question. 2 lines are going to be parallel if their direction vectors are scalar multiples of each other. So I know that this line, it passes through minus 2, 1, 4, and there'll be some multiple of the direction vector, which is, well, it's parallel to this one, got to have the same direction vector, 2, 1, minus 2. What about if it's perpendicular? Well, 2 lines are perpendicular if the dot product of the direction vectors is equal to 0. So we no longer can say they multiply together to give negative 1, because it's not slope anymore, it's not 2 dimensions. We're playing with vectors, and our condition for perpendicular and vectors was they multiply together to give 0. Alright. So I know 1 minus 1, 4 dotted with, well, the one I'm trying to find. I want to find the direction vector that's perpendicular to this. So A, B, C, I've just called it. So I know A minus B plus 4C must equal 0. I need to find numbers that fit this. There is the answer. I just don't know what A, B, and C are. So 0, 2, 3 plus some multiple of A, B, C will equal some multiple of 1 minus 1, 4. Well, let's play around with that. The x ones give me that lambda a is mu, the y ones give me that 2 plus lambda b is minus mu, and the z ones give me that 3 plus lambda c is 4 mu. 3 equations, 4 pronumerals. Oh well, let's keep going with it. So 2 plus lambda b is minus lambda a. So I've got that lambda is minus 2 on a plus b. The next playing around with it, so grouping it a bit differently, I get that lambda is 3 on 4a minus c. Well, they're both lambda, so they must equal each other. So I now create this new equation. 11a plus 3b minus 2c is equal to 0. But remember, we've already found that a minus b plus 4c is equal to 0. Multiply that by 11, I can eliminate the a's. Eliminate them, Okay, I now know that B is 23C on 7. Do I have more information? No, I don't. So I'll just let C equal 7. Because remember, it's going to end up any multiple. I can pick any number I like. I picked 7 because it makes B a nice, neat whole number. So if I let C equal 7, B becomes 23, A becomes -5. Okay, I've got a direction vector. Right? So the key reason this works is because remember it's times some scalar multiple. So I could actually pick any number I like for C. We know this. If two lines have direction vectors B1 and B2, then we know they're parallel if one is a scalar multiple of the other. That's certainly true. And they're perpendicular if the dot product equals 0. Skew lines, we don't have these new things, skew lines. So skew lines are any lines that are not parallel but also do not meet, which is weird. In 2 dimensions that's impossible, but in 3 dimensions it's possible. Okay. So it is possible for perpendicular lines to also be skewed. We have to show that these two are indeed skewed lines. So we've got to show basically there's no point of intersection. That's the key thing to skewed lines. There's no point of intersection. Show there's no point of intersection. Okay, let's create some equations. Well, if they are going to intersect, then 1 plus lambda would equal mu, 3 plus lambda would be 4 mu, minus 1 would equal 5 mu. Okay, all these would be true if they intersect. Well, if I equate 1 and 3 together, I would get that mu is minus 1/5. Now 1 plus lambda is equal to then minus 1/5. So if that's true, lambda is minus 6 on 5. Okay. But when I equate 2 and 3, what happens? Well, equate 2 and 3, lambda becomes minus 19 on 5. And that's not minus 6 on 5. And lambda's got to be the same for all of them. And so if it's not the same for all of them, they can't intersect. If they don't intersect, they're skewed. I didn't bother about the not parallel because clearly the direction vectors are not multiples of each other. So the parallelness of it is trivial. Now you might want to mention something about it, but I've mentioned it in my answer that they're not parallel. But it's easy to see. The key really is the not intersecting part there, and we've proven that. All right.